Okay, everyone, welcome to the secure two-party computation session. We're going to start with one method, secure reductions, on the concept of converting correlations from one side. Mahimna Kelkar, Varun Narayan, and Riyad Safar, and Riyad Safar.
Thanks for the introduction. So I will talk about one method secure reductions. This is a joint work with Vali Shine in the culture and so I'll start with some motivation. Secure two-party computation allows two parties to jointly compute a function over the combined data while keeping their local data in secret. And while it is a very general and strong tool, it is quite accurate in both computation and communication. So a way to common paradigm to mitigate this cost is to use correlations, which are samples of some joint distribution, and these correlations can be generated in an offline phase before the inputs are known, and can speed up the online phase. So one example of such standard correlation is the autocorrelation. So here we have two parties, a sender and a receiver. One party gets two random elements from some sets, which I will refer to them as secrets, and the other one gets one of them random plus the index of the secrets. So using techniques like OT extension, which is a way to take small amount of OT correlations and from them generate a lot of OT correlations, and they are very cheap to generate. And also, while this correlation is universal in the sense that it is computationally suffice to compute any function, sometimes it is more efficient to use a specially crafted correlation for the specific function that you are trying to evaluate. This can really make the online protocol much more efficient. And so there are many correlations that we want to use, but we don't know how to use to do it as efficiently as the OT correlation. So we will be interested in converting one type of correlation into another, and it is especially interesting us when the source correlation can be generated very cheaply, like the OT correlation. So I will talk about two correlations, the two-free correlation and the free-two correlation. So both are really useful for converting secret shared bits over Z2 to be over Z3 and vice versa. And this type of functionality is needed in a type of MPC-friendly symmetric primitives that Hugo talked about in his distinguished lecture, that kind of mix different linear operations over different moduli. So conversions between OT to these kind of correlations have been done before, but we wanted to do it even more efficiently. So the problem of converting between different types of correlations has been studied before, but for the case where there is no communication between the parties, and as intuition suggests, this model is quite restrictive, and there are a lot of conversions that are probably impossible. So we take the next step, correlation with a single unidirectional message. We call this a one-message secure reduction, and this one message actually dramatically changes the landscape in terms of usability. So using OT and using information theoretic garbing, we can convert into any type of correlation. So the question that we ask is the efficiency. So I will set up a few notations. There are m copies of the source correlation XY. We want to generate n copies of target correlation NV. The parties actually generate n copies of some output correlation U hat V hat, and require correctness. So the n copies are actually statistically close to n copies of the target correlation. We want the sender to be semi-honest, so we will follow the protocol. And as for security, intuitively, we want that the in expectation for each of the parties, in expectation over the reviews, each party will know nothing more about the other party's output more than it should have had given this output correlation. And this is formalized using the expectations. Okay, so I'll summarize our results. So we construct a general rejection sampling-based technique for OSR with OT and source correlation. Using this technique, we construct completely efficient OSR, converting OT correlation to useful special correlations, which again are the correlations that are used for these MPC symmetric primitives. we also show several lower bounds. So using a measure called S star from the information theory literature, which I will define later in this talk, we show that OMSR requires a linear amount of communication in the number of output copies if S star of the source is strictly smaller than S star of the target. And this holds for many useful OMSR instances. So we also show that even with two-way communication, converting OT to a random secret shared unit vector requires a linear amount of communication in the next optical vector. So actually, these two lower bounds hold even without any security. And common randomness in the real world can be generated very cheaply. And using these common randomness without the security, we can do it without any communication. But we show here that for OMSR, using common randomness is pretty much useless. So if we enhance the source the parties with common randomness in the secure version, these lower bounds will still hold, but without security, we can do it without any communication. Okay. So let me start with our construction, and I will first define what is an accept reject protocol, which is a stepping stone towards our OMSR construction. So suppose that by conditioning on some event, which is dependent only on the view of the sender, the two parties can do some local computation and output the required target correlation. So the sender, if the event falls, which happens with probability O, the sender will send a single accept symbol to the receiver, and the two will do the local computation and be happy. But if not, he will send a reject symbol, and the two will abort. And also, we mentioned that in order to use it for OMSR, we need this protocol to be perfectly secure in the sense that I described earlier. Okay, so how can we use it for OMSR? So the idea is to use batching. So the sender will look at batches of K copies, and she will go over them one at a time, and she will check that each of the K copies in the batch are accepting in the accept reject protocol. When this happens, she will send the index of the first batch that it happens, and both parties will run the accept reject protocol on each of the copies in the batch. So this message is actually a geometric kind of variable, and it can be compressed down to its entropy, and it will result with expected asymptotical amortized communication cost of log 1 over rho, where rho is the accept probability. Okay. So let's build one. So it's an accept reject protocol converting OT over Z3 to two-free correlation. So first of all, what is the two-free correlation? It's basically two random signatures of the same bit, where one is over Z2 and one is over Z3. So the X's are over Z2 and the R's are over Z3. So I'll set up a few notations to help us around. So we will define a function R sub x1 r1 of x to be the unique value of r0 when x0 equals x. And we also define the vector A sub x1 r1 to be evaluating this function on 0 and 1. So the main idea is basically we want the receiver to output his index and secret, and the sender will output something such that whatever the output is actually a random two-free correlation. So what we will do in order to force it to happen, so the sender will accept if his secrets are the vector A for some x1 r1. And this happens with probability of the two firsts. Sorry. Okay. And what would be the local conversion? So given the event happens, the sender will output x1 r1, and the receiver will simply output the index and this will result in an OMSR protocol with a symptotical amortized communication cost of log 3 over 2. Okay, so we have a few optimizations over it. So it turns out that we can exploit the fact that the event is only dependent on the sender's view by using the same OT correlation until it is accepted. So this can be done in the following way. So instead of using a lot of short string OTs, we will use only n long string OTs and split them into blocks. So instead of the batch to be k copies of the short string OT, we will actually use k blocks of different correlations. And whenever a batch is rejected, we will simply move to the next block in each of these correlations. We can also improve the probability of acceptance. I won't go much into the details, but basically the idea is that we can play in a single bit and double the probability of acceptance. This can be done in some cases. And the transformation that I showed before actually achieves expected guarantee for the communication and computation. But it turns out we can modify the protocol a bit and achieve a worst case guarantee, but with a negligible probability to abort. So this is a table that shows what different values of the batch size does for the OSR. So taking a bigger batch makes the probability of acceptance in all of the copies exponentially smaller. But as we can see here, we can choose a fairly small value of k, which is the batch size, and we will save up most of the communication, while the computation is not too bad. I showed the accept reject protocol for 2-3 correlation, but it's a fairly similar construction for the 3-6. So this OSR can be plugged in for several MPC-friendly 2PC. And as we can see, we cut the offline communication by over the factor of 2. And these primitives have many applications. For one example is the length doubling PRG. And it's very helpful in many scenarios. But one application for that is the function signature neural network, which is a framework for secure evaluation of a neural network. So our work cuts the end-to-end communication for the radius gates by 1.5. Okay, so now I'll go over the lower bounds. So I'll first define what is an S-star. So an S-star of a correlation XY is defined as the supremum of the mutual information between U and Y over the mutual information between U and X. And this supremum is taken over all of the random variables U that are generated from X. And the theorem I will show now is again without any security, so it's for OMR and for all the stars without security. So amortized communication cost of formal converting the correlation, the source correlation XY to UV is strictly positive if S-star of the source is strictly smaller than S-star of the star. So I showed the proof outline. So first of all, we notice that amortized communication cost of OMR converting source correlation XY to common randomness is at least 1 minus S-star. And this is obtained by modifying seminal working information theory about common randomness capacity. And then we show that even using a linear amount of copies, we can get as close to this bound as we want. Okay. And now, so I want to lower bound the OMR for converting source correlation XY to a target correlation UV. So let's say that we have a lower bound using the source correlation XY of generating n copies, n bits of common randomness with communication of Cn. And we can, using the target correlation UV, generate n bits of common randomness of C prime n. This is using only kn copies because of our second statement. So we learn, since we have a low bound of Cn, we know that the communication of this conversion, that we first convert to kn copies of UV and then convert common randomness, must be at least Cn. And we get a bound for alpha, which is the amortized communication cost for the OMR converting XY to UV. Okay, so we then compute S-star for several correlations. So for example, S-star of 1 out of part of KOT over any domain is exactly 1 over K. And with that, we can achieve a lower bound of half and a third of our results. We also show lower bounds on interactive reductions. So again, I will say the theorem using OT, or actually a broad class of source correlations, to converting these to a random signature unit vector equals a linear amount of communication in the length of the vector. So this is done in 2 steps. First, we show that any interactive protocol for deriving a random secret length and unit vector using a correlation XY with L bits of communication can be turned into a non-interactive protocol for deriving N bits of common randomness with communication of about 2 to the minus of L success probability. This is shown by tweaking a non-result but by a canonical. And on the other side, we show that lower bounds on non-interactive agreement. So we show that using any correlation XY with S star less than 1, which calls for many correlations, including the OT correlation, agreeing on N bits of common randomness succeeds with only probability of 2 to the omega minus omega of N. This is a generalized theorem of Bogdanov and Drossel, which we generalize using generalized upper conductivity inequality and all those inequalities. So we were using this two statements, we have a linear lower bound of L. And we also show that so common randomness does not help with ORSR. So basically, we take an ORSR with error of epsilon and show that there exists a realization. So sorry, the error. So it's an ORSR with common randomness, and we want to convert it into another ORSR without this common randomness. So we first show that there is a realization of the common randomness such that conditioned upon the privacy error will still be comparable. So square root of epsilon. And then using a Markov chain convergence theorem, we show that also the correctness should hold with an error of n squared times square root of epsilon. So if epsilon is negligible, then this is also will be negligible. So I wrote a little poem. It's totally me about MPC. And yeah, thanks.
This looks.
I don't know what you're thinking about.
You don't know? Okay, do you have any questions? Please come from. So in the ML application that you showed, did you use the one with the arrow? Is there?
Actually, our construction achieves. So we have two constructions. We can think of it as a perfect with expected communication, or worst case communication, but with a negative probability for both. So you can take other one.
Okay, let's thank you again. Thank you so much.
Thanks.
Okay, next we have the framework for statistically centered private OT with optimal rate. from Pedro Franco, Nico Nothing, and Marcel Ivan Hassan, and Pedro is good.
Thank you. So I'm going to talk about SSPOT with rate, and this is joint work with Nico and actually. So let's start with the definition of OT. OT is a primitive between the receiver with an input bit P and the sender with two input bits and 1. And at the end of the protocol, the receiver should get N. In terms of security, we want that the sender knows nothing about the receiver's bits, and that the receiver learns nothing about the other ones, M1 minus. And it's well known that OT is a well-established primitive in cryptography with lots of applications, especially in 2PC and MS. So in this talk, we're interested in the communication complexity of OT. And what's the best communication that we can get from an OT scheme? If we think of the insecure protocol, we have two options. Either the sender sends both M0 and M1 to the receiver, or the receiver sends the bit P and gets M bits. In both cases, we have two bits being communicated, which means that for K OT executions, we need at least 2 K bits of communication. We say that an OT scheme has optimal rate if its communication complexity approaches this lower bound for a large enough number of OT executions. So the first question we can ask is whether there are OT schemes with optimal rate, excluding trivial FAG-based solutions. And this question was answered affirmatively in a paper at Eurocrypt last year, where a scheme from DDH and LPM. However, this scheme only provides semi-owned security against computationally bounded adversaries. So a natural follow-up question is, what is the strongest security that we can get from an OT scheme while maintaining optimal? This is the question that we tackle in this way. Okay, so the security that we consider in this work is called statistical sender privacy, or SSP. And in SSP, the sender is still computationally bounded and semi-honest as before, but now the receiver is computationally unbounded and malicious. And formally, this is captured by the existence of an extractor that extracts the input of the receiver, such that sending M0 and M1 is statistically indistinguishable from just sending them. And there are numerous reasons to consider this notion. First, from a theoretical point of view, this is the strongest security that we can achieve in 2 rounds and in the plane model, so no random oracles CRS. And also, SSPOT has a lot of applications to construct like more complex primitives, such as statistical zaps or non-linear. Okay, so our main result in this work is a new 2-round SSPOT with optimal rate in the plane model, for which security holds under the DDH and the LPM assumptions. And in particular, these assumptions are not meant to imply FAG. So what does this mean? It means, in terms of security, it means that sender security holds statistically against malicious receivers, and receiver security holds under the DDH and the LPM assumptions against semi-honest. So this is the SSP property, and in terms of communication, it means that the total communication of our protocol approaches 2K for large enough K, where K is the number of OT executions. All right. So our work builds on top of this previous one, which I'll refer to as BBDP. And in BBDP, they start with the following units. The LPM assumption, a rate 1 linear homomorphic encryption scheme. private information retrieval with sender security, and this new primitive called co-private information retrieval, PIR, and which I'll explain later what it is. So they first show that we can combine these ingredients to get a notice scheme with optimal rate with semi-security. Then they proceed to instantiate these building blocks from the DDH assumption. And this implies notice scheme with optimal rate from the DDH and the LPMs. At a very high level, they start with download weight 1 OT, which can be built from a weight 1 linear element encryption scheme. And this is a notice scheme where the sender's message has already optimal size, but the receiver's message is still large. Then they show how to use LPM to do a re-encryption step that compresses the receiver's message down to weight 1. And finally, they're using the LPM assumption. So this introduces some errors in the receiver's output. And they show how to combine PIR and co-PIR to correct this. Okay, for our construction, we still need the LPM assumption. And our first observation is that if we replace these building blocks on the left side by their statistical counterparts. So if we replace the weight 1 LAG by a malicious one with statistical circuit privacy, and if we replace the PIR and the co-PIR by their SSP variants, then the same transformation with a few tweaks here and there implies an SSPOT with optimal. So to get our final result, we need to show that we can instantiate these building blocks from the DDH. Malicious weight 1 LAG can be obtained from the DDH assumption by plugging known results from previous works. And the same goes for SSP PIR. But for SSP co-PIR, we know nothing apart from trivial FAG-based solutions. So to get our final result, we need to build an SSP co-PIR from the DDH. And this is what I'm going to show you for the remaining of it. So let's start with the definition of co-private information retrieval, or co-PIR. This is a primitive between a receiver, which inputs a set of indices I1, IT, and the sender, which inputs a database name. And at the end of the protocol, we want the receiver to get the database key with a few positions erased. And these positions correspond to the indices I1, IT. In terms of efficiency for our purposes, we want a two-round scheme where the receiver's message is of size independent of the database of the sender. And we want the sender's message to have size very close to the size of the database. So we want the sender's message to be very small. And in terms of security, we want that the erased positions of the receiver, the erased positions are hidden from the receiver. In the statistical variant, we want these positions to be statistically hidden. And we want the receiver's input to be hidden from the system. So the reason why SSP co-PIR was not known before is because previous co-PIR constructions all relied on functional PRFs. And PRFs only provide computational security. They only provide pseudo randomness. They don't provide statistical randomness for functional points. So in this work, we take a different approach and we provide new constructions for co-PIR, which are SSP from the DDH assumption. The first one is based on rate 1 SSP PIR. And then we show a more efficient one with improved computational complexity from all the one loss functions. So these constructions share very similar ideas. So today I'm just going to talk about the one based on PI. So first, what is a rate one PIR? This is essentially a PIR with some additional properties. And in a PIR, the receiver starts by encoding an index I into a query Q. And this query should hide the index. The sender inputs a database, and this database can be decomposed into blocks D1, Dn. Given the query Q and the database D, the sender can compute a PIR message, and we assume that this message can be decomposed into a header and the block which encodes the I. And later, the receiver can encode the I. In terms of efficiency, we want this block to be exactly of the same size as the block BI. And we want the header to be of constant size, so independent of the size of the database. So this is the rate one property. And for SSP, similarly as before, we want that there is an extractor that extracts the index I from the query Q, such that sending D is statistically indistinguishable from just sending DI. And we know that PIR with these properties exists from the DDH assumption from previous. So first, I'm going to show you how to use rate one PIR to build an intermediate primitive called one query co-PIR, which erases only one position of the database. So the sender starts with the database D and computes these intermediate databases, which are equal to D, except that they have one position erased. So D1 has the first position erased, D2 has the second position erased, and so on. The sender inputs the concatenation of these databases into a PIR and gets this PIR message. And by the PIR correctness, we know that this block encodes DI, which corresponds to D with the IF position. So we erased one position. Well, if the PIR is rate one in SSP, then the resulting one query co-PIR also has this properties. However, this scheme only erases one position, and for our application, we need to erase several positions. So to bootstrap this scheme into one that erases multiple positions, we'll do the following. So given T queries from the receiver, the sender inputs the initial database into the first co-PIR and gets an encoding of T with one position erased plus a header. Then it takes this block and it inputs this block into the next co-PIR. And we get an encoding of D with two positions erased plus another header. Then we recursively apply the same procedure. And at the end, we get an encoding of D with T positions erased plus T headers. Since the underlying one query co-PIR is rate one, then all these blocks are of the same size. Or in other words, there's no blow up in the communication after recursion. So as long as we have sublinear number of headers, then the final message is rate one. And we obtain a rate one co-PIR that erases a sublinear number of positions. And finally, SSP security follows from the SSP security of the query co-PIR. Okay, to wrap up, in this work, we built a two-round SSPOT with optimal rates from the DDH and the alternate assumptions. And our main ingredient is a new SSP co-PIR from the DDH. And an interesting open question is if we can get a OT with optimal rate just from the DDH. Thank you.
So there's a lot of complications. And we're waiting. Can you tell us how you use peer and co-peer to reduce the error? Because you did that.
So yes, so the LPN introduces errors in the receiver's output. We use co-PIR to erase those positions with errors. Yeah, the receiver knows the position. And then they use PIR to get the right output in those positions.
Questions? Let's take this again.